welcome to this talk. I'm V.S. Subramanian from the Computer Science Department at ISTS, and it's my pleasure to welcome a former student of mine at the University of Maryland, John Dickerson. John did his undergraduate work at Maryland, spent 2 years working in my lab after he finished his degree, and then was, found that Carnegie Mellon offered him fantastic opportunities, including, amongst other things, building the computational foundations required to figure out how to do kidney exchanges in a fair, and efficient way. So the code that he's written for this is based on a fairly rich mathematical theory, which involves a multidisciplinary approach involving computer scientists, clinicians, economists, and powers one of the major kidney exchange organizations in the country today. So John, over to you.
Thank you, VS. So like VS said, I'm John Dickerson. I'm a now second-year assistant professor at the University of Maryland. And today I'll be talking about using optimization, computer science, machine learning, that kind of thing, to balance fairness and efficiency, both of which I'll define in something called kidney exchange. Okay. So I like to start off with this motivational quote. Markets come in many forms, some of which don't conform to conventional notions of markets, and some in which money may play little or no role at all. And this is a quote from a guy, Al Roth, who wrote a book. This is a sort of popular science book called Who Gets What and Why. But Al Roth is a well-known economist who received a Nobel Prize for some of his work in matching markets. And kidney exchange is going to be a type of matching market. So what are matching markets? Matching problems, prices don't do all or even any of the work. So we may not have prices, or we may have prices, but they may not have as much power as they might have in, say, a financial market. Okay? So in these markets, in these problems, agents are going to be paired with other agents or other groups of agents, transactions, or contracts. Okay. And here are some quick examples. The sort of canonical matching market example is matching workers to firms, and this is something that everyone in this room has gone through. So I went through it when I got a job as an assistant professor. Those of you who are tenured here went through it when you got jobs as professors. Those of you who are students will go through it when you either go on the academic market or the industrial market. This is matching workers to firms. Matching children to schools. This is sort of a hot topic from time to time based on a different sort of political agendas. This is the problem that's known as school choice, right? So you have a child, you have a set of children in a city, you have a set of schools. These children or their parents have preferences over schools, the schools have preferences over children, and so on. How do we match them up such that we don't, put too many kids in a room, and so on? Matching residents to hospitals. This is a fairly famous example. It's the Match, the National Residency Matching Program. So once per year, doctors, a different kind of doctor than I am, the useful kind of doctor, they'll graduate from med school and they'll get matched to a residency program. Okay. Matching patients to donors. We'll talk about that in depth in this talk. Matching advertisements to viewers. So I'm in a computer science department, and we just have a brand new building that is getting built right now at the University of Maryland, and it was paid for essentially by matching advertisements to viewers, right? So a lot of revenue in tech firms comes from this, how do I match eyeballs to advertisements such that we say maximize revenue and obey some other constraints. And finally, matching riders to rideshare drivers, right? So Uber, Lyft, Didi, etc. These are all examples of markets where money isn't doing all of the work. And in fact, in some of these, there is no money involved at all. So somebody who wants to design or analyze these markets, we may consider various dimensions of sort of analysis. One of these is going to be uncertainty, right? So we live in an uncertain world. What do I mean by uncertainty? Well, one might be, does a matched edge in these markets truly exist? And when I say edge, I mean, well, let's represent an agent as a node. And an edge between these two agents is going to represent, say, a potential transaction between them. So here we have a problem from Upwork, which is an online labor marketplace that matches workers to firms. Workers are going to arrive in an online fashion, and firms may extend an offer to those workers, but when they extend that offer, that edge, they don't know if it truly exists. The worker might reject it, say. Similarly, when I'm a worker and I arrive in this market, I don't know if my edge to a firm is going to exist because, I might not have the right skill. I might not know Java, or I might not know how to do some sort of math, or I might not have the right background in international policy, whatever. There might not be an edge that exists. We might also ask, hey, how valuable is an edge? How valuable is a match? Right, so let's take the setting where we're Facebook or we're DoubleClick acquired by Google, and we want to show an advertisement to a viewer. And we've determined that, hey, I can actually show this advertisement to this viewer. I don't know how good it's going to be, right? So let's say that I'm Bugatti, and I want to show an advertisement to my eyeballs. Well, my eyeballs are going to be worth less than, say, VS's eyeballs, right? Because I'm going to be less likely to buy a Bugatti.
I think the probability for me.
Similarly, we might ask about long-term uncertainty, right? Will a better match arrive in the future? So let's go back to our Bugatti example. You know, do I show this one advertisement to John right now and exhaust my budget, or do I wait until the future and maybe there's a 50% chance that Bill Gates is going to come into this, New York Times website or whatever, and then he'll buy a Bugatti, and there's a 50% chance that he won't. How do I maximize revenue? Another dimension might be competition, right, between different matching markets. So here we might have rival matching markets like Lyft and Uber, and they're going to compete over the same set of agents. And these agents are going to be, say, in the rideshare case, riders, me, et cetera. But they're also going to be rideshare drivers. So a lot of Ubers that I get into, the driver is driving for Uber and Lyft for various reasons, right? So as a firm, I might ask, how does this affect global social welfare, right? So let's say that I'm the mayor of, I don't know, DC, and I'm asking, hey, should I regulate, should I add tax? This is actually something going on in DC right now. There's a discussion to add more taxes to Uber and to Lyft, to rideshare in DC, because it's been shown to, say, maybe hurt metro ridership. It might hurt public transportation. How does this affect global social welfare? And let's say that I'm one of these firms. How do I differentiate in such a way that, say, I stay alive if I'm the smaller player, or so that I can, say, put the other person out of business, the other firm out of business, and then do better overall? One other dimension might be match cadence. Okay, so let's look at dating markets, right? So we have Match.com, OkCupid, Coffee Meets Bagel, and Tinder. We might ask, how quickly do edges form? Right? Am I swiping right to form an edge, or am I going on Match.com and writing an essay to somebody, which takes a long time to form that edge? How frequently does a market clear? Right? Is there some sort of centralized matchmaker, like Fiddler on the Roof with Yunta Yunta, who once a month matches people? Or am I matching in a decentralized fashion very quickly, like in, say, a market like Tinder? And finally, let's look at dating markets again. Can agents re-enter the market? Right? So after I match, do I find love forever? Or do I find love for 2 or 3 years and then re-enter the market? How should that enter into my equation when I'm doing things like pricing or clearing and so on? Okay. So the general idea here is we have these 3 dimensions, and there are many others. I'll talk about a few others. Fairness is one of these. We have these dimensions that we want to use data and optimization alongside human domain expertise, basically to learn these matching policies or maybe pricing policies if money is involved. And they're going to rest on strong theoretical underpinnings that are going to provide us with design guidance and runtime guarantees. And so that's where some of the optimization, computer science, and machine learning comes in, as well as pure mathematics and economics. That's sort of the underpinning thesis behind a lot of work in market design, matching market design, mechanism design, and so on. Cool. So in this talk, I'm going to talk about 3 dimensions of matching market design. Managing short-term uncertainty. Okay, so this is going to be does that edge exist kind of stuff that I talked about earlier. Balancing equity and efficiency, balancing fairness and efficiency for a couple different definitions of fairness. And finally, combining human input and optimization to learn a dynamic matching policy. Okay. And each of these is going to be supported by my work with a large nationwide kidney exchange, along with some early stage work with some folks in Europe. And if we have time, which we might not, I'll leave you with some open problems in this space. Okay, so this is a short talk, and it covers recent and ongoing work. You can feel free to talk to me offline. And in fact, this is a small enough audience that if any of you just want to ask questions, I'm happy to just chat with you. Cool. So before we go into defining this example that I'm going to use throughout the talk, kidney exchange, are there any questions? Okay. So in the US, about 100,000 people, give or take, are waiting on a wait list for a new kidney. So when you have kidney failure, there are 2 ways to stay alive. One is to receive dialysis, which is a basically mechanical method that takes blood out of your body, filters it, and puts it back into you, or to receive a new organ from somewhere. And dialysis is a very expensive, in terms of quality of life and also in terms of dollars, treatment for kidney disease. And so the preferred method is to receive a new kidney from somewhere else. So in the US, there are these 100,000 people who are waiting for a new kidney. About 35,000 are added every year. Between 4,000 and 4,500 or so will die while waiting. So this is every year, and this is an unfortunate sort of reality. 14,000 to 15,000 of these people will receive a kidney every year from a deceased donor. So this is a cadaveric donor. This is somebody who has, say, I'm a kidney donor on my license. They get into a car crash, unfortunately, and their organs are harvested quickly and then dispatched essentially locally to somebody who's on a waiting list in a very well understood sort of prioritized way. Okay. About 5,500 or so will receive a kidney from a living donor. Right? So receiving a kidney from a living donor is preferable in general because these living donor kidneys tend to be more powerful than deceased donor kidneys. Okay? So you have somebody who dies, you take the kidney out of their body, it waits outside of their body for a while, and it degrades pretty quickly over time. So after about 24 to 48 hours, most surgeons won't actually put a kidney into somebody else's body. So these living donor kidneys are actually a lot more powerful in general. And so most of us in this room actually have, say, 2 kidneys, and we would be living just as good of a life, essentially, if we only had one of them. And so if we find a medically compatible match, a logistically compatible match, then we can give our kidney to somebody else, and that person receives a kidney, and they go away happy. Okay? Now, kidney exchanges are going to be one method for finding a logistically and medically compatible match. And it's a relatively nascent market. The first organized market like this was organized in about 2004 up in New England. Well, I guess we're in New England, by Al Roth and some folks at the time Harvard and BU. And we'll talk about that in greater depth. So in this talk, I'll talk about my experience with the United Network for Organ Sharing Nationwide Kidney Exchange, which has about 160 transplant centers here in the US. And we'll use some data from the National Health Services, basically version of UNOS over in the UK. Cool. So what is a kidney exchange? Well, here's the most simple kidney exchange that you could imagine. On the right side, we have these 2 patients who need a kidney. They have end-stage renal disease, and they have paired but incompatible donors. Okay, so let's say that the wife is willing to give a kidney to her husband, but she has the wrong blood type. So blood type is a hard constraint that you just can't fix with all the money in the world. Similarly, the brother here has a brother who's willing to give him a kidney, but can't because he has the wrong tissue type or whatever. There's some medical reason. So in a world where there's no organized market, where we can have these people meet up and possibly swap donors, both of these patient-donor pairs would leave with no kidney. The idea behind a kidney exchange is to instead form an organized market where these patient-donor pairs can enter and then try to find a donor of some other patient who's medically compatible with that person. Okay? But that person's only going to give, let's say the wife is medically compatible with the brother and the brother is medically compatible with the husband, that wife is only going to give to the brother if her paired patient receives a kidney from somewhere else. Okay? So she's willing to give to the brother if and only if the husband receives a kidney, potentially in a 2-way cyclic swap like this, maybe from the brother, or you can imagine, say, a 3rd patient-donor pair or a 4th patient-donor pair forming some sort of cyclic swap that's more elaborate. Okay. So in practice, these sorts of cyclic swaps, where a patient gives to a donor, whose paired patient gives to a donor, and so on until it flips back to that initial patient, they're limited in length in practice to about 3 or 4, typically. And it's because all these surgeries have to happen simultaneously. Okay? So in all countries, except I believe Iran, you can't enter into a binding contract that says if you do X or if you give me some number of dollars, then I will give you an organ. Okay? So in practice, these have to happen simultaneously because let's say that the wife gives to the brother and the brother has a handshake agreement to give to the husband next week. Well, that guy is under no legal obligation to give to the husband next week, and he can leave the market. Okay? And in that case, the husband is strictly worse off. His wife has given a kidney, but he hasn't received a kidney in return. Okay? So his bargaining chip is sort of out of the window. His wife is strictly worse off than before, and he's as bad as he was before. So in practice, transplant centers all organize these surgeries simultaneously, and that's sort of a logistical nightmare beyond, say, 3 or 4 patient-donor pairs, because you have to have 8 operating rooms and 32 different nurses and all that kind of stuff. So as a computer scientist or an economist, we can view this as a graph optimization problem, where every patient-donor pair, yeah?
I'm going to ask a question. This may be a detail, but surgeries are often canceled for various reasons.
That will be the short-term uncertainty that we'll be trying to manage. Yeah, absolutely. Yeah, so a variety of reasons exist for these vertices or these edges to disappear. And that's a huge issue in all kidney exchanges. Yeah. But we'll get to that in maybe 3 or 4 slides. That's a great point. Yeah. So in this talk, we'll be talking about a directed graft problem where we have a patient-donor pair represented as a single vertex, and then we have a directed edge from the donor at the first vertex to the patient at the second, if that donor could potentially give to the patient. And then we're interested in finding these sorts of cyclic swaps. In this case, we would find a 2-cycle in this graph. And it may or may not exist for a variety of reasons. Now, a second structure that we'll be interested in finding is something called a non-directed donor-initiated chain. And these occur when somebody walks into an exchange and says, well, I have too many kidneys inside of me. I'd like to give one to somebody. I'd like to save a life. And so they're interested in paying it forward. They don't have a paired patient. So they come in and they give a kidney to a patient whose paired donor gives a kidney to a patient whose paired donor gives a kidney to a patient, and so on and so on and so on. And these are very powerful tools. And in fact, in modern kidney exchanges, they drive most of the efficiency results. Okay? They can also be executed non-simultaneously. And to see why that is, say that we execute this non-directed donor to a patient, and then tomorrow we do a donor to a patient, and then the next week we're going to try to do this donor to a patient, but this donor gets sick and can't give to the patient anymore. Okay? So that breaks this edge right here. Nobody is strictly worse off now. This patient here, who didn't get a kidney, still has a fully intact donor. Okay? So in practice, these can occur over many years even, and can be 30 or 40 or 50 in length. But because of these failures that were already brought up, an edge might not exist, a donor might leave the market, et cetera. In practice, these chains are typically capped in the planning range, at 10 or 20. Cool, so in terms of real-world impact, it's only about a decade old, this kidney exchange concept, maybe a decade and a half now. But it already accounts for over 10% of living donations in the US. It's also a worldwide phenomenon. There's a European cost action right now to try to hook different European kidney exchanges together. It's slowly moving toward this organized international exchange. Okay, so maybe a worldwide kidney exchange in the next few years. And I've worked extensively with the United Network for Organ Sharing, UNOS, US Nationwide Kidney Exchange. The number rises and lowers sometimes. It's around 160 transplant centers. It's over 2/3 of transplant centers in the US participate in this. That's completely autonomous biweekly match runs, so it's a nice shout out to AI. And by autonomous, I mean the matching is autonomous, not the actual surgeries. And it's the only automated exchange in the US like this. Cool, so taking a step back, today we'll be talking about solving the clearing problem, right? This is to find the best for some value of best disjoint set of cycles with some length cap, 3 or 4 in practice, and chains. Okay, and I say disjoint because we can't have a vertex participate in 2 different cyclic swaps because then that donor would lose both kidneys, okay? And you can imagine generalizations where we have 2 donors, but today we'll be assuming there's only 1 donor per patient-donor pair, okay? So a quick example of the problem we're trying to solve is, let's say that we were doing maximum cardinality clearing here. Well, we could match this long chain here, and then these two cycles here, and everyone would leave with a kidney. Okay? So typically the cycle cap, like I said, is, let's say, around 3. Okay, so it's 3 at UNOS, it's 3 at most exchanges, sometimes it's 4, and the chain cap can rise all the way up to, say, 20 or 30. It can be quite long. The problem itself is NP hard. For those of you from the computer science world, it's NP hard for basically any reasonable parameterization of the problem. So if you allow only tiny cycles, then it's really easy to solve. But if you have even the most basic version of best there, maximum cardinality, just match the most number of people. Who cares about weights? Who cares about uncertainty? It's hard in theory, and it's also really, really hard in practice. There's a big stack of literature from the econ, operations research, and computer science world trying to solve these problems. Okay? But it's important because they're actually, these are fielded algorithms. Cool, so here's a simple integer program to solve this problem, where we're saying best is going to be maximum weight matching, where we don't care about the future, we don't care about any sort of uncertainty, but we have weights attached to the edges that say how good, say, a transplant is going to be. Okay? So associate with every cycle and chain, a 2-cycle, a 3-cycle, a chain of length 12, whatever, there are a lot of these. Associate with every one of these cycles in chain C some binary variable xc. Okay? It's going to take the value 1 if we're going to use that cycle or chain. It's going to take the value 0 otherwise. Our goal is to maximize, across all the different matchings M, our utility for that matching. And what's that going to be? That's just going to be the sum over all the different cycles and chains that we use of the weights of the cycles and chains. Subject to a single constraint that says, for every vertex I, take all the cycles and chains that I belongs to, and you can use only one of them at most. Okay, so you can use none of these, you can use one of these. You can't have a vertex I that appears in more than one cycle or chain that you use. Right? So this is a really simple thing to write down. Like I said, there are tons of these variables though, right? So if chains of length 20, there's like O of V to the 20 or O of V to the 19 of these. So you can't write this down in memory. There's a lot of work about solving this problem, but I'm going to make the claim that this optimization problem isn't even sort of the thing that you should be focusing on, right? Instead, we should be focusing on a bigger problem, which is what is best? What should I be maximizing here? Okay. Should I maximize matches right now, or should I maximize them over time? And how do I, do this trade-off between over time and right now? Should I maximize transplants or matches? So like was mentioned, a lot of these algorithmic matches will fail for a variety of reasons, and maybe I should try to match the number of people who actually have a kidney put into them as opposed to the number of matches that occur. What sort of prioritization scheme should I use? So the medical community has their own opinions on who should be prioritized. Economics has their own opinions on who should be prioritized. Ethics has their own opinions on who should be prioritized. How do I incorporate all that stuff into this? What sort of modeling choices should I make? Should I include incentives, transplant center incentives, patient donor incentives, countrywide incentives in, say, an international exchange? What about ethical considerations? What about legality? What about money? Should I include any of this, right? So it costs money to put a kidney into somebody else. I'm going to make the claim, and we can argue about this offline if you want, that optimization, machine learning, et cetera, they can handle all of this stuff if we can formulate it, but it may be inflexible and it may be hard to understand for humans. So our high-level thesis, our high-level sort of what we want, is we want to keep humans in the loop at a high level, and then we want to let fancy machine learning, fancy optimization techniques implement whatever these humans want at the low level, handle that implementation process. Cool. So before we jump into our first of sort of 3 deep dive sections in this talk, any questions? Okay, so I'll talk a bit about managing short-term uncertainty, which is a question that comes up pretty immediately in most of these talks. So getting matched does not mean you're going to get transplanted. Let's say you're in a kidney exchange and you hear, hey, I've been matched to somebody. That does not mean that you're going to get a kidney, which is unfortunate. So at UNOS, for instance, only around 10 to 15% of matched structures result in an actual transplant. Okay, that's a high failure rate. And by failure, again, I want to emphasize this doesn't mean a kidney goes into somebody and then it fails. This means that they've been matched algorithmically and then they do not get a transplant. Okay? But still, this is bad. 85%, let's say, of matched structures involve a failure. Okay, there's a similarly low percentage at other exchanges. And this goes up and down based on policy and medical testing, but there's a high failure rate. There are a lot of reasons for this. One is that medical testing is just imperfect. One is that these exchanges compete with other exchanges. They compete with the deceased donor waiting list. So I can be matched, and then I can get an offer from the deceased donor waiting list, and maybe I'll take that, and then I break a cycle, et cetera. We might ask, though, how do we handle this using, say, optimization? One simple way would be to encode the probability of transplantation onto every edge in the graph. Okay? So let's say that we somehow have knowledge of these probabilities. I know that there's an edge from VS's donor to me, but it exists with only probability 0.6. Because there's a 40% chance that his donor is going to leave the market for some reason. Okay, so we can encode, alongside that edge weight, we can encode an edge existence probability, rather than just say feasibility. And what this does is it gives us a new sort of utility function for every edge, every potential transplant. It also gives us a new utility for every cycle, every chain, and every full matching. Okay. So we can define a new clearing problem, where here we're changing our view of best to, instead of doing maximum weight or maximum cardinality, now it's maximum expected cardinality. Okay, so we match a bunch of cycles and chains, some edges fail, and then we only get points for the structures that exist after these failures. So if I have a 3 cycle and one of the edges fails in that 3 cycle, I don't get points for anything, right? That completely crumbles the entire cycle. If I have a chain and the 3rd edge fails in that chain, I only get points up to where that edge failed. So now we're interested in finding the matching M star with highest discounted utility. So again, to drive this point home, let's say that we have 3 patient-donor pairs, 1, 2, and 3. We know with pretty high probability these edges from 1 to 2 and 2 back to 1 exist. And then there's this risky 3 cycle that we could take, where there's only a 0.1 probability that an edge from 2 to 3 exists and from 3 back to 1. So if you look at the expected utility of these, you have 2 vertices times basically 0.81 probability that this exists, or you can match 3 vertices times whatever 0.9 times 0.1 times 0.1 is. So one of these has higher expected utility. But then if there are weights on these edges, and this is a really high weight, maybe you would end up matching that anyway, right? And so that's more of a policy decision. Cool, so the max cardinality matching is going to pick this really unlikely 3 cycle. A maximum expected transplant sort of matching is going to probably pick this 2 cycle. Well, we might ask ourselves, hey, that was just some tiny example that John put on a slide to try and prove that this could make a difference. Is it going to make a difference in a large market? And we have some large market results basically saying, hey, in sparse random grafts that look a lot like kidney exchanges, for any failure probability, for any failures that you associate with these edges, there's going to exist a matching that is linearly better. It's much bigger in terms of expected transplants than any maximum cardinality matching that you give me. So to put that another way, if I give you a graph, a compatibility graph, and I ask you for your favorite maximum cardinality matching, the matching that has the most number of vertices in it, I can give you a smaller matching that will result in many more transplants than expectation. So this is sort of a case against maximum cardinality matching. And all of the kidney exchanges early on started doing basically maximum cardinality or maximum weighted matching with no sort of principled approach to handling uncertainty like this. So in practice, we solved this, and this isn't sort of an optimization talk, so I won't go into details here, but in practice, we solved this via some combination of ML and traditional OR techniques. So we solved this big IP using branch and price techniques. This makes the problem a little bit harder if you are into branch and bound and branch and price and operations research. This makes some parts of this process a little bit harder, including these failure probabilities, right? This is a more general form of the kidney exchange problem that we started off by talking about. But it also makes some really difficult problems easier. And we can talk about offline how to solve these. I mean, I have a bunch of papers on this. But in the interest of time, I'll just talk about sort of the results on real UNOS data about when you implement sort of a more general but more accurate form of clearing. So here we have some results from like the first 5 years or so of the United Network for Organ Sharing Kidney Exchange, which booted up in October of 2010. On the x-axis, we have a match run. So here's the very first match run, where we had a compatibility graph consisting of real patient-donor pairs, and then a market was cleared. And some people got some transplants, and then they came back into the market, and so on and so on, all the way up to about the 160th match run. And this is up to about 400 by now. On the y-axis, we have the number of expected transplants for 2 different ways of clearing. One is the deterministic method that doesn't take into account these failure probabilities, and the other is a probabilistic method that uses a really rough estimate of what those edge failure probabilities are going to be. Right? So it's hard to estimate whether or not an edge exists. It's hard to get that p that I associate with an edge. So what we did is we just looked at a bunch of data and applied a reasonable constant edge failure rate of 0.7 to every edge. And that gives these results. So if you see a bar that's just tan, it means that the red and the tan got the same number of points. And you can imagine some matchings. Say if there's only one matching in the compatibility graph, then every matching algorithm is going to choose basically the same optimal match. But some match runs actually have a huge gain from probabilistic matching. Okay? And so what's happening there when you say deep dive down into the actual graph that's being solved here is deterministic matching will choose an extremely long chain. So I think in one of these there was like a 19 length chain, whereas probabilistic matching is going to endogenously trade off matching all of those people in a long chain and maybe doing a shorter chain and some smaller cycles that are more likely overall to execute. Okay, and that's all taking place behind the scenes in the optimization side. And in fact, when you do a little more data mining and associate with the edges a more realistic edge failure probability, say in this case, associating with sicker patients a higher failure rate and with healthier patients a lower failure rate, these gains become just tremendous. And these bars, I mean, these are huge gains in terms of scale. And that's just true because we have a very high failure rate in these markets. Okay? Yeah.
Are these, I'm trying to think, this is also, as you're going to probably talk about later, this is a dynamic problem.
Yeah.
Over time.
Yeah.
So these calculations assume if there's a failure,
Yeah.
you've lost it.
Yeah.
That's not really true. You're going to have another chance.
Absolutely, yeah. So this is short-term uncertainty we're talking about. The third part of this talk is going to be talking about how we combine this short-term management with dynamic matching. So say you're matching once a month or once a week, how do we incorporate that into, so we basically do like a reinforcement learning approach to doing this.
So this could kind of overstate the benefits because...
Yeah, so these results are, and in fact, we've seen this in reality, and this could be a much longer discussion. Amongst most exchanges in the US, the match rate has decreased. So UNOS actually started once a month early on, then went to twice a month, then went to once a week, and now it's at, I think, twice a week. And that's in part because matching really quickly allows you to just test more edges. So if they're not going to exist, why not test more? And I'm going to make the case that says, hey, why are we doing these matches? Why not do some like strategic testing of edges such that we can sort of combine both. So if I know that you're a really high failure probability vertex, then I should test a bunch of edges going into you before I do this match run even to begin with, right? And then I should pick an edge that exists. And in fact, that's what we're going to talk about right here, which is our idea here is to perform some small amount of costly testing prior to this match run, to test for the non-existence of edges prior to doing this algorithmic match. So there is some cost associated with basically picking out of a compatibility graph a set of cycles that may or may not actually go to transplant. So in an ideal world, we would be able to pre-test whether or not these edges exist, and then only pick the edges that do exist, right? We can't do this for every single edge, though, right? So one thing you have to do before a transplant is something called a cross-match, and that's a physical, basically, mixing of bloods to see if they congeal. And so in a graph with v vertices, we have O of v squared edges, and that means a lot of blood to take out of a patient, basically, and you would have to do this basically, I think, once a month. We could also ask, hey, surgeons, if we propose to you a possible transplant, will you actually do it? We could ask them that ahead of time, because in practice, you can see about 30% of edges that you know fail because the surgeon rejects the transplant. And this is one example of why this might happen is, let's say that I need a kidney, and I'm 31. I could get an offer from somebody who's, say, 85, and my surgeon would say, well, all things considered, I think you're going to get a better offer if we keep you in the pool for 2 weeks, and so I'm going to cancel this 85 offer. And that might crumble an entire cycle, and it's a very bad thing. So I could actually just phone up my surgeon beforehand and say, hey, would you actually do this transplant? And she would say no, and then I wouldn't match that to begin with. Okay, but we can't do that for every edge. So we cast this as a stochastic matching or a stochastic set packing problem, where our problem is now, given this compatibility graph G with our patient-donor pairs and our edges that may or may not exist, we'd like to choose some small subset S of those edges to test. And we're going to get results saying, yeah, that exists, or no, it doesn't exist. And our goal is to, on that small subset of edges, find a matching that's really close to what we could have done if we knew every edge existed, if we had omniscient sort of knowledge. Okay. And we actually have a really nice sort of fundamental stochastic matching result that's revising resubmit right now at operations research that says, hey, on the 2-cycle problem, we can actually do this. We can actually basically get optimal by only matching a constant number of incident edges per vertex. So 4 or 5 or 6, depending on basically a couple little things. But again, not an optimization talk, so I'll show you what this might look like, again, just in the static case, not in the dynamic case, on data from UNIS. So here on the x-axis, we're varying that edge failure rate that we are only estimating. We don't actually know what this is in practice. Okay, from 0, all the edges exist, to 1, nothing exists. On the y-axis, we're showing the fraction of omniscient matching we can achieve. Okay, so if I knew what every edge existed, I knew what every vertex existed, I would be able to do x. I don't know which vertices and edges exist, so I'm only able to do y. It's the fraction there. This big black bar is that algorithm I showed you earlier, the discounted clearing problem. Okay, and sort of intuitively, as edge failure rates increase, I'm doing worse and worse and worse. If I'm allowed to test even one edge going into every vertex, I get a 21% bump relative to omniscient. 2 edges, I get a little more bump. 3 edges, 4 edges, and 5 edges. I get these huge sorts of gains just by being able to tease out a little bit of knowledge from this graph by doing 1 test per vertex or 2 tests per vertex. Okay? So this is sort of a nice policy message, which we can again collapse into the more dynamic world, which says, hey, even doing 1 or 2 of these extra tests, picking up the phone and calling my surgeon, or doing a couple blood tests is going to result in potentially huge gains in efficiency. Cool. So in theory and practice, we're helping the global bottom line in a static setting by considering this post-match failure explicitly in the optimization problem. But is that going to hurt some individuals? Right? I talked about how in practice, when you have a sicker individual, probably they have a higher failure rate. So are we going to end up marginalizing these already sort of marginalized patients? And I'll just give a high-level overview of some balancing fairness and efficiency work we've been doing with some very simple rules. We can talk offline about some ongoing work I have that appeared at AAAI and is under submission now at NIPS. Cool. So I'll talk about fairness in the context of what's called a highly sensitized patient. So a highly sensitized patient is somebody who's unlikely to be compatible with a random donor. Okay, so I'm highly sensitized for the point of this talk if, say, it's unlikely that I would be able to match with even 1 person in this audience. Okay, so pick a bunch of random donors from the United States. Maybe I'm only going to be able to match with 1 out of every 1,000, something like that. So on the deceased donor waiting list, people waiting for a cadaveric transplant, the number of highly sensitized patients hovers around 15 to 20% of that list. In kidney exchanges, this number is much higher. Okay, so it's about 60%. What I'm showing here is, again, maybe the first 180, 100, first 200 or so match runs at UNOS. I'm showing the percentage of the pool that is highly sensitized. So in red here, we have highly sensitized patients. In tan, we have lowly sensitized patients. Green are these non-directed donors, these altruistic donors, and they get used up really quickly. And you can see that this hovers right around 60%. This black bar here is hovering right around 60% of the pool is highly sensitized. And that's the case for a couple of reasons. One is that the deceased donor waiting list just has more throughput. So if you're likely to get a match, you're going to get it probably via the deceased donor waiting list. In kidney exchanges, at least early on, we're seeing a sort of a Hail Mary attempt to get these people who are highly sensitized to get matched. And so they build up in the pool over time. So we're going to talk about balancing efficiency and fairness via sort of a well-defined metric called the price of fairness. Right? So this efficiency versus fairness trade-off is a classic problem in economics, where we have utilitarian objectives, match the most number of vertices, maximize the weight. And they're going to be basically objectives that favor certain classes at the expense of marginalizing others. Whereas a fair objective, quotes around fair, is going to sacrifice some of that efficiency in the name of, say, egalitarianism or some other type of fairness. So some folks from the operations research and computer science worlds simultaneously defined this price of fairness, which is the relative system efficiency loss under a fair allocation rule. Okay, so we have an efficient system that's maximizing matches, and we put a fair rule into play. How much efficiency do we end up dropping because of that? That's the price of fairness. We can apply this to the kidney exchange problem. Remember, our goal here is to find some optimal matching M star that maximizes some utility function, just any old utility function U. The price of fairness here is then going to be the relative loss of match efficiency due to using some fair utility function. So we have our utilitarian function U that maximizes, say, matches. We have some fair matching function U of F that, say, gives 10 times the amount of weight to VS getting a match, something like that. And we are going to ask, how much utility do we lose in terms of utilitarian utility on the optimal match based on how much utility we get from, say, this fair match, right? So if the fair match gives me 2 points and the efficient match gives me 4 points, then I'm going to have 4 minus 2 over 4, and that'll be half. I've lost half my efficiency. So the goal here, sort of the ideal would be to find some sort of fair matching function that has 0 price of efficiency, no efficiency loss whatsoever. I'm able to do a fair allocation, and I still match the most number of people, something like that. And you can do theoretical analysis to show that, hey, in some pretty strict classes of utility functions, we're actually able to find low price of fairness matchings in random graph models. But this fairness criterion is extremely strict. That's interesting. The theoretical assumptions that people make traditionally in these sorts of matching market results are pretty not natural. So these are big, dense graphs, right? These are graphs that tend toward infinity, which is hopefully something that kidney exchanges won't do. They're dense, meaning that there are lots of edges that exist between people. And in the medical case, these graphs are actually sparse in practice. This result is in terms of cycles without chains. We've actually, my PhD student just extended this to a result with chains, showing that if you have enough altruistic donors, the price of fairness actually tends to 0. There's no post-match failures. This isn't a dynamic model. There are simplified patient-donor features, and so on and so on and so on. So we might ask, hey, what's the price of fairness in practice? And for this talk, and in general when I talk to, say, folks in the medical community, we know that it's important basically to work within or near to constraints in the fielded system. So you can't make really big changes in terms of medical policy. Okay? And that's motivated by this great operations research paper by Bert Seamus et al. Talking about their efforts to change the deceased donor matching policy at UNOS, and also with our experience working with the living donation system within UNOS and some other exchanges. So in this talk, I'll present basically 2 super simple, super intuitive rules that are parameterized ways to bump some sort of fairness into this market. One is going to be lexicographic. We have a bunch of vertex types. We have highly sensitized and we have non-highly sensitized, and we're going to strictly prefer one over the other. And the other is going to be an implementation of basically the system that's used in practice that says, hey, if you're of a certain class of marginalized patient, then we're going to give you a little boost on your edge weight. So if your name is John, you get plus 25 points. Not a real rule. So lexicographic fairness at a high level is going to say, hey, let's find the best match that includes at least some fraction of highly sensitized patients. Right? And so these are general methods. I'm presenting them to you in the kidney exchange setting. So we are able to say match 50% of the highly sensitized patients across all matchings. And I want to find some matching that includes at least some fraction of those. It's a matching-wide constraint, which means it breaks a bunch of our optimization solvers, right? It's saying across all the possible matchings, I need to just basically cut off the ones that don't do a certain thing. That's actually pretty hard to do in a discrete optimization problem like this. It's a strong guarantee on match composition, which is nice, but it might be harder to predict the effect on economic efficiency. We could talk about an even more intuitive matching sort of utilitarian function, or sorry, fairness-based utility function, which is going to take basically the edge weight going into any highly sensitized patient, and it's going to bump it up by some factor beta. Okay, so if I set beta to 1, then I'm going to value highly sensitized matches at twice what I value lowly sensitized matches. It's just a reweighting on my input graph, which means any solver you're using right now, you can just use for this problem as well. But it might be hard to find a good beta, right? Should I choose 0.1 or 0.9 or 1.1 or whatever? And you can do two things to try and find out what this beta should be. One is you can do an empirical exploration, right? We have a lot of computers. We can just run a bunch of experiments on simulated kidney exchange data to tell you what the price of fairness would be like in a realistic setting. And two is I have some work with some folks at Duke that just won an award at AAAI, which is a big AI conference, that talks about how we aggregate human value judgments to actually set a value like this. So just some quick pictures. If we look at UNO's data again, using this weighted fairness rule, as we vary failure rates from 1, which is nothing exists, to 0, which is everything exists, we can look at, for reasonable edge failure rates, where we associate with more sick patients higher failure rates, with less sick patients lower failure rates, the impact on total efficiency as we increase the weight that we put onto these highly sensitized patients. So on the x-axis here, I'm showing the expected transplants to the marginalized class as I increase weight. And you can see that more people get transplanted, more marginalized candidates get transplanted, but there is some impact on overall efficiency, right? And so these are the sorts of, this is what's called a Pareto Frontier, basically, for this beta parameter that goes into weighted fairness. And these are the sorts of pictures that I find can be very impactful from a policy point of view, because you can say, hey, I can point to this 1.0 here, and that's about where I'm gaining a lot of, say, marginalized candidates, but I've lost a very little amount of overall efficiency, something like that. And that's a very ad hoc method, so we have some ongoing work that tries to do a more principled approach to basically, and all of you are going to have a different point. Somebody's going to say, well, we should be here. Somebody's going to say, no, let's be here. How do we aggregate our sort of noisy opinions into an objective function? We can talk about that offline. Cool. So earlier we saw that this failure-aware discounted clearing problem, this sort of failure-aware matching would result in a tremendous gain in number of expected transplants. Remember those red bars versus those tan bars. That gain is going to come at a price, though, right? It may further marginalize these hard-to-match patients because highly sensitized patients tend to be matched in long chains. They don't have a lot of edges going into them, so they tend to be matched in these like 20-length chains, or not matched at all. And they tend to have higher failure rates because there are typically other health problems, typically, with these highly sensitized patients, right? Luckily, what we can do is we can, again, use sort of experimental analysis along with some of this random graph analysis to determine what values of beta we would even be willing to accept, right? So here I'm picking on the x-axis different edge failure rates. Here's a realistic edge failure rate in the 0.5 to 0.7 range. And I'm plotting the gain of this failure-aware matching versus deterministic matching as we increase the weighted fairness from 0 all the way up to 10. So that beta equals 10 says that I value a transplant going into a highly sensitized patient at 11 times what I value it going into a lowly sensitized patient, which is a very high number. And we can see actually by adding in this failure-aware method, even when we do like this hyper sort of prioritization, we end up beating deterministic matching by a pretty huge percentage anyway. So I haven't told you how to select a beta, but I have said, hey, it looks like we can use this beta to balance out some of the marginalization that comes along with the efficiency gains of a better method failure-aware matching. Cool. So fairness and efficiency can be balanced in theory in our nice general model that takes into account edge failure and weights and things like that in a static model. But how should we learn to match over time? Right? The world doesn't end tomorrow. I shouldn't maximize my matches right now. The world goes on and on and on. So here I'll talk about learning to match in a dynamic environment, and I'll give a very high-level overview of some stuff we're doing. So kidney exchange is a naturally dynamic event, right? It can be described by the evolution of its underlying compatibility graph. where additions and removals of edges and vertices happen over time, right? Somebody comes in, they get matched, they leave the market. Somebody comes in, they die, unfortunately, they leave the market. We test an edge, it doesn't exist, it disappears, and so on, right? Here's a chart of some reasons why things come in and things come out. You know, somebody dies, we have an altruist who runs out of patients. They say, hey, I've been waiting in the pool, I want to give a kidney, you haven't matched me for 2 months, I got to go back to work, I got to get this on my mind, I'm out. So we should ask, how should we balance matching now versus waiting to match? And toward that end, in I guess about 2015, I started working on a framework called FutureMatch, on my framework called FutureMatch, which is basically a general framework that learns to match in a dynamic environment. Okay? So we split this into 2 different segments. One is going to be a heavy offline learning portion, which we're going to run once or periodically, let's say once a month. And the other portion is going to be run online. Okay, so the offline portion, what we're going to do is we're going to use domain experts to describe an overall goal. We're going to take historical data and this policy input to learn some sort of weight function for individual edges. Okay, so how good is an individual transplant going to be, irrespective of anything else? We'll take some historical data and create a graph generator that's going to be seeded with these edge weights. Okay, it's very realistic. And then we're going to use this generator and a realistic simulator, which is open source, it's online, I can show you how to use it. And we're going to learn potentials for graph elements as a function of the exchange dynamics. And that's a bunch of words that I'm going to talk about in a few slides. But it basically is a way to do approximate dynamic programming, think reinforcement learning style approaches, to learning a good matching policy that maximizes a utility function over time. So that is a big learning process. It takes a lot of effort. Then online, what we're going to do is we're going to use these potentials that we learned offline. We're going to combine them with our real edge weight function in a very simple pre-process to a graph that then gets fed into a maximum weighted solver, a static solver. And by doing all this learning here, but then crumpling it down into an edge weight, we're able to basically get the same runtime of a static solver while incorporating some knowledge of the future into that sort of solution process. So it's a happy medium. Remember, even the static problem here is super hard to solve. So we can't really do online solving of this problem. Cool, so I'm just going to go step by step through this framework. Let's start with an objective. Let's say that we've gotten all of our policy experts into a room and they decided, hey, we want to maximize the expected graft survival rate of kidneys that we put into people, subject to some sort of prioritization schemes, fairness, and so on. Okay, so what you can do is, once people have decided on that, you can learn survival rates for different grafts. You can do your sort of standard data mining stuff from the health community. So here's a graph where we learned survival rates from all the living donations since about 1987, which were a few short of 100,000 by now. And you can see that not all transplants are created equally. Okay, so here's something called HLA. You can think of it as a vector of 6 different variables, and if they match perfectly, you're happier than if they don't match perfectly between a patient and a donor. And what I'm showing here is what's called a Kaplan-Meier, something called survival analysis, where we have on the x-axis graft survival rate. So this is a kidney that lasts in a body for 0 days, 1,000 days, all the way up to about 9,000 days. And on the y-axis, we're showing the fraction of kidneys that last that long. So if you have an imperfect match, kidneys fail a lot faster than if you have a perfect match. And you can imagine a lot more features than just this going into an edge weight function. So you can go off to your favorite group of medical doctors and ask them what things matter, what should be incorporated into this edge weight function, and then you can just do it. So have experts decide on this and then translate it into an edge weight, W, that sits on a transplant or an edge and then gets matched. We also need some sort of graph generator. It's basically, it gives us a prior that we can draw from, right? It's a generative method that allows us to pick out graphs that look a lot like what kidney exchange could look like. So for these results, I did about 300 plus match runs from UNOS data. Here's a couple snapshots of actual real UNOS data. This is the very first match run. You can see it's very sparse. Now it's a bit hairier. We feed this into, again, a realistic simulator. We can talk about that offline. And now we want to basically learn how to match such that we maximize an objective over time. Okay. So people are familiar with sort of Markov decision processes, partially observable Markov decision processes, some of the recent work in, say, deep reinforcement learning. That's the kind of stuff that could go into this, okay? So that full optimization problem, where we maximize an objective over time, very hard. The realistic theory, very complex, very difficult. There's been some nice work out of groups at Stanford and MIT and Columbia on this recently, but it's still, you can't implement it in practice. Trajectory-based methods aren't going to scale here. This is sort of the go-to for dynamic optimization. So what we need to do is we need to have an approximation. And here's an idea. We want to associate with every element type in a graph its potential to help the objective in the future. Okay, and that potential is going to be a real valued number. And we have to learn them. And then at runtime, once we've learned all this stuff, we combine our potentials with the edge weights and perform just a myopic maximum utility matching. But now these potential edge weights, these potential aware edge weights, are going to combine some future awareness into that myopic matching at no runtime hit. So let me just give you a quick example of a potential. So given a set of features theta representing structural elements in your optimization problem, in this case a graph, vertices, edges, cycles, whatever, subgraphs, a 2-cycle, a 3-cycle. We want to learn the potential p theta for every type theta, and that's going to quantify the future usefulness of an element, okay, of a 2-cycle or a 3-cycle. So for an example, let's let theta be the combination of 20 patient-donor blood types. So we have an O-type patient with an O-type donor, an O-type patient with an A-type donor, da-da-da-da-da. And then we have an O altruist, an A altruist, a B altruist, and an AB altruist. Okay, so 16 patient-donor blood types for altruistic donors. And intuitively, there's some structure to this problem. We know, for instance, that O-type altruistic donors are probably more valuable than A-type altruistic donors because O is the universal blood type, or universal donor blood type. So all things considered, probably an altruist who has O-type blood is going to be able to give to more people than an altruist with A-type blood. So we can constrain our optimization problem, do a bunch of other sort of neat optimization tricks to learn these potentials. Okay? So online, we can just adjust our solver to take these potentials into account. So say we've learned that an O-type altruist has potential 2.1, whereas a patient-donor pair, where the patient has O-type blood and the donor has AB-type blood, which is very difficult to match. AB can only give to AB, O can only have from O, has a very low potential of 0.1. Then we're going to take every edge between an O-type altruist and an OAB pair, and we're going to take its edge weight, say 1, and we'll subtract off some potential to help in the future. And now we're going to get a negative edge weight here. It says basically, if we have an O-type altruist giving to an OAB pair, we're going to have a negative edge weight here. And what that is going to do is it's going to force chains that come out of, say, an O-type altruist to be long enough to offset basically the negative weight. So we're not going to have an O-type altruist who's wasted on a single patient-donor pair. Instead, we're going to force the myopic matching algorithm to use longer chains in this one specific case. Okay, and we can take into account the learned edge weight function there. But the goal here basically is after we've done this hardcore learning process, we're able to do an edge weight pre-process on the graph and have no or low runtime hit. Cool, so some quick experiments. We show it's possible to basically increase the overall quote-unquote efficiency, which is the number of transplants a lot, at a much smaller decrease in marginalized transplants. We show it's possible to increase the number of marginalized transplants a lot at basically no quote-unquote price of fairness. And kind of interestingly, we're able to show that you can increase both the number of transplants that go to everyone and the number of marginalized transplants relative to the deterministic baseline. And that sweet spot's going to depend a lot on your distribution, but luckily we have access to a lot of data. We sort of know how these exchanges work, and so we're able to learn this. Okay. So we now use results from that for recommendations at various exchanges. Cool. So I guess in the last few minutes, I'll talk about some cutting edge results in the organ exchange world. So you can move beyond kidneys to livers, for instance. It's a similar matching problem mathematically. We have only one liver though, so what you end up having to do at a very high level is slice a liver up from a donor and then put it into somebody else. And there are various ways to do that slicing that are more valuable but also more risky. Nobody's fielded a full liver exchange yet. It is a riskier process. There are fewer people who need a liver than a kidney, but that would be interesting to see. We could actually move into multi-organ exchange. And so this is work that just appeared at JAIR. And the basic idea behind this is chains are really great. These altruistic donations are really, really great. They drive efficiency in matching markets right now a ton. And this has been motivated from econ, from medicine, et cetera. Kidney transplants are easy and they're popular. There are a lot of altruistic donors. Okay, a lot of them. It's very nice. Liver transplants are higher mortality and higher morbidity. And in turn, there are essentially no altruistic donors who walk into, say, a hospital and say, I want to give a slice of liver to help somebody out. But we want to somehow use these chains that have to be initiated by an altruistic donor to increase efficiency. So a possible idea would be to take a kidney donor who's altruistic, give to a patient who needs a kidney, whose donor is willing to give a kidney or a liver to somebody in a kidney exchange, whose patient needs a kidney, whose donor is willing to give a kidney or a liver, who can then give a liver slice to a patient who needs a liver, whose donor is willing to give a kidney or a liver, and so on and so on and so on. And there are ethical issues here that I'd love to talk about. But what this does is it allows us to use these sorts of very powerful chain-link structures to match people in a liver exchange without actually having liver altruistic donors. In the interest of time, I'll skip this. You can also do lung exchange, which is pretty interesting stuff. And finally, you can start talking about things like game theory and mechanism design in this space. So clearinghouses are going to care, like UNOS, are going to care about global welfare overall. How many patients am I matching over time? What's the quality of my patients that I'm matching over time? Transplant centers, however, might care about their own individual welfare as well, right? How many of my own patients receive kidneys? And they're going to care about this because of prestige, because of money, or maybe they're going to balance that between that and global welfare. Patient-donor pairs are going to care about their individual welfare. Did I receive a kidney? But most of the time, they just go in and they trust a surgeon to make a decision for them. So this introduces some interesting issues into kidney exchange. One is that we've been talking about our compatibility graph as one unit. I know the full state of the world. I know the altruistic pairs that altruistic donors that exist. I know the patient-donor pairs that exist. I want to do a matching on all of this. In reality, different transplant centers sort of own different patient-donor pairs. So here we have JHU, quote unquote, owning 3 people who live in Baltimore who registered at JHU and an altruistic donor. Okay? And what they're going to do is offline, they might match people internally. For instance, JHU, and I'm just picking on JHU here, it's not a real thing, might match this altruistic donor going to a patient-donor pair, going to another patient-donor pair offline, and then show to the kidney exchange only those pairs that it couldn't match. Remember, it's incentivized to match internally. But remember, at the beginning of the talk, on this exact same compatibility graph, we were able to match everybody if we knew the whole graph. If, say, this hospital does this, then we can see these vertices. We can end up matching this 2 cycle, but these guys go unmatched. Okay, so there's an efficiency loss because we don't have an incentive-compatible mechanism. We're not incentivizing transplant centers to tell us about all their patient-donor pairs. So if I just asked offline, how many patient-donor pairs are given to a central clearinghouse from a single transplant center that could be matched internally? Well, would anybody want to guess? So over time, we interact with a bunch of transplant centers, and they give us patient-donor pairs, and then we look at what they could have done internally. How many, like, what percentage of pairs do you think they actually show us?
20%?
Close. This is a I think this is a result from like 2015. I haven't checked recently, but they strategize a lot. Okay, so they're matching internally a lot. Basically, they only give those people that they can't match to the central clearinghouse. And there's theory behind this. There's empirical results behind this. That's hurting efficiency a lot. So it'd be great to have results in that space, and I'd love to talk to you offline about that. So if you have ideas, hit me up. And that's it.
Thank you, John. Questions? So I have a question.
Yes.
So anytime I see something like this, I look and say, how could I, as so people, there are malicious actors out there. In this case, I wouldn't even call these actors necessarily malicious. There are actors who would like to maximize their self-interest in a way that subverts your system, right?
Yeah.
So have you thought about the vulnerabilities of this protocol and how somebody can basically hack it? I don't mean
Interesting.
cyber hack it, but take advantage of vulnerabilities of the way the protocol is designed to achieve their ends in a way that.
I've only really considered.
I'm not asking you to tell me the answer. But
Yeah, well,
did you do it?
basically none of the answers to like the mechanism design incentive stuff are known in kidney exchange. This is all open research. So my answer to you is going to be no. I have no idea what they would do there. The thing is, you're not going to like empty someone's bank account by hacking into a kidney exchange. So.
But all they need is one kidney.
Oh, I see what you're saying. There's a lot of human-in-the-loop stuff that would have to go on here. So there'd be a lot of sort of social engineering as well, because at the end of the day, you are actually taking a kidney physically from a human and putting it into another human. So people have not looked into something that probably is interesting to people in this room, the interplay between, say, kidney exchanges and various black markets. And there is a lot of research on this. the interplay between kidney exchange, and there are markets where you can legally buy kidneys as well. For instance, in Iran, there are 2 markets where you can legally enter into like a binding monetary contract to get a kidney from somebody. None of that research, as far as I know, has really been done.
Still illegal for Americans.
Yeah, don't do that. Yeah.
So when you mentioned your fairness constraints, you mentioned like two different constraints, demographic and weighted. So I was curious, what other fairness constraints you have considered, and why did you pick these 2?
Yeah, not many. So we picked those because those are easy to explain basically on a single slide. And I say that's not a cheeky response. It's important to be able to explain these things to people who aren't computer scientists or machine learning people. We haven't considered the more, and there's been a little bit of work from the pure econ literature. There's a 2006 paper in Theoretical Economics, I think, that looks at like Lorenz dominance, stuff like that. But that's in a pure theory model. There hasn't been that much work looking at like the general sort of equality of opportunity, equality of outcome kind of FAT-ML style approaches to doing with, and that would be very interesting here, especially as we move into more of this dynamic sort of matching reinforcement learning stuff. So that hasn't really been looked at yet. Yeah.
That's actually a very similar question. Are there incentives to lie, to give false information?
Like as a surgeon to give a different tissue type vector or something like that?
Or the patients to exaggerate some attribute in order to get it.
Yeah.
And suddenly they discover right before the surgery. So I wonder how that could
So I haven't seen research on this in the kidney exchange world. I have definitely seen this. The one that pops to mind is, I think, liver donation, deceased liver donation. You're prioritized higher on the waiting list the sicker you get.
Yes.
So you can lie about that to move up the waiting list. As far as I know, it's not as explicitly easy to do that in kidney exchange, but yeah, by all means, you probably could.
And then wonder about how to design the mechanism to make lying.
All of this, right? So we were only talking about the transplant centers as agents, but patients and donors, countries, et cetera, these are all agents that have their own incentives. Insurance companies, right? That's one I didn't even bring in, so yeah.
I'm just curious about, and I don't work with large data quite in this way, but I'm just curious about the role of the experts here. Were they brought in mainly to give you the sort of fairness weights? Or it seems to me, because a lot of times we think we're experts and we get stuff wrong.
Yeah.
Or is this just to give you a starting point for your simulation?
So it's a really ad hoc process. And UNOS is interesting in that it's transparent about everything by mandate. And so you can actually look up exactly the policy that's used, the priority points that say, John gets 25 points. Or in practice, it's like if you end a chain at the same transplant center, you get 100 extra points. If you're this level of sensitization, you get this number of points. If you're on the waiting list for this long, you get this number of points, and so on. It's like a big, basically additive function, and then that gets plopped onto an edge weight, and then you do a maximum weight solver. And all of that is not decided on in a reasonable way. And it just isn't. So it's exactly like you would expect. You have a giant conference call, and people say, well, I think this should be 25, this should be 50, this should be 100. And you do a little bit of sensitivity analysis using some of the experimental results here, but at the end of the day, it's ad hoc.
So you run it, but you really are getting these fairness weights from the experts.
Correct.
Okay.
Yeah, so there's some feedback that comes out. And so part of closing the loop on that FutureMatch sort of framework, yeah, it's very unsatisfactory. None of these are actually principled approaches to doing that utility function design. And so we have some early work on that. Actually, a lot of people in the AI community are sort of getting into this right now. Moral Machine is a famous one out of MIT Media Lab that's trying to do this for self-driving cars. That says, hey, how do we actually set this thing given a bunch of people's noisy opinions?
Right.
And that's a problem that's computer science, ethics, AI, like everything. And you can plug that in as well. Yeah.
John, you had mentioned how important the altruistic donor was. Have you done, or has anybody done work to, in fact, look at taking that 4,000 to 4,500 people who die and being able to change that by actually adding a price function to this to a donor?
Price function, like, what do you mean by price function? So you're saying take a cadaver and start it?
Like a donor would say $10,000 for your breed.
Yeah. So in these talks, I don't go into the money world because that's an opinion that runs the gamut, especially in academia, right? Between like microecon, who we're going to think, well, a price is going to solve all these problems, and it's going to solve all these problems. It's going to introduce a whole boatload of other problems, and so yeah. And that's the long and short of it. So you worry really about coercion, and different countries take different approaches to coercion. So Germany, off the top of my head, is one that's really, really afraid of coercion. In fact, I think it's illegal to give a living donation to somebody who's basically not your brother, your mother, your sister, or your wife or husband. So I think like second cousins can't even give it because they're worried about coercion. And that's explicitly because I don't even know if you're slipping me $10,000 in Bitcoin or whatever, right? It would solve a lot, like supply would certainly increase. It's not clear that that's the right thing to do. Again, this is a human value judgment aggregation problem. Yeah.
All right, well, thank you very much again.